All right, thank you. Thank you for the introduction, and I'm really grateful to have this chance to introduce, to give a talk in this wonderful workshop. So today I'm going to talk about a little bit different qubit compared to the previous two talks. And so in the previous two talks, mainly the qubit Professor Oliver and Professor Qidong Chen using is transmon. So today I'm going to talk about a different type of qubit, which called fluxonium, and then I want to do a little bit review or kind of take a look at what's the recent development of these fluxonium type of superconducting qubits. Okay, all right. So we all know that, well, like in 2019, Google already announced these quantum supremacy, and then they achieve with these 53 qubit quantum processor, and then also for the IBM last year, at the end of last year they announced 1,121 qubits quantum processor, and so they have really like a big roadmap in order to reach 1 million qubits. And so it looks like all the qubits development is quite mature, but I want to mention that all these is all being achieved by transmon superconducting qubits. So one question is, well, if transmon is good, then the one question is actually, is there anything that we can do even like better with a transmon, or actually can do something different with a transmon? So in order to talk about that, I just let me put a little bit, little introduction, and thanks to Professor Oliver that he already introduced this. And so actually a transmon qubit actually it's typically it's a Josephson junction shunted with a larger capacitor, and so therefore the potential that it looks like it's non-harmonic, so it's a nonlinear oscillator such that the energy spacing between the eigenstates are not equal spacing. And so therefore you can use it as a qubit such that you can confine the dynamics into, for example, 0 and 1 transition. Okay, and so this is one of the transmon that we made in Tsinghua University. And so here it's pretty simple. You have two big pads acting as this capacitor, and then you put a Josephson junction at the middle. Then this actually is a transmon. So there are pros and cons, and so let me just put some of my comments over here. One is this circuit. It's quite simple. Basically, you just shunted a Josephson junction with larger capacitor, and also it's quite simple for fabrication. There's the process is relatively simple compared to, for example, fluxonium. And then also it's already been highly optimized such that the process and also the shape, it's been optimized with the past many years. And so therefore there's a lot of group that can achieve more than 100 microseconds coherence time for transmon qubits. And then it already been demonstrated that the multi-qubit quantum processor is possible with the transmon qubit. However, there are something coming, and so I listed as a pro and con. The one is this simple transition right here. It looks like the transition is quite relatively simple, and so the transition that you can use, it's quite limited, because if you want to go to a higher transition, the transition dipole or the matrix element to those higher transition is quite small, and so you're not too much. I mean, there isn't too much that you can use for that. And then also the selection rule, because these eigenstate looks like, or the potential looks like simple. So the selection rule for engineering is quite limited. And so there are some, so this simple one is, the transition is simple so that you can protect it nicely, and then you engineer it nicely because it's simple. But also the usage of that is limited. So I listed it as a pro and con. For the con is like there's no intrinsic protection for the spontaneous emission for this 0-1 transition right here. As long as you put the 0 and 1 into a background such that you can do the spontaneous emission, then this transition will happen. And then so you need to engineer the environment such that you can protect this spontaneous emission nicely. The other one is the low anharmonicity. So for transmon, in order to make it insensitive to the charge noise, so people typically put a large capacitor right here. So it sacrifices the anharmonicity, which is the transition frequency between 1 and 2 and the 0 and 1. Typically, the difference is around like 200 or 300 megahertz. So it's quite low. So the bad thing about this is if you want to drive your transition with a larger with high power microwave drive, well, it could because the low anharmonicity, so that you can accidentally excited some higher transitions. Okay. So with that, then let me start to talk about today's topic. Then basically this is outline. So let me just use an alternative superconductor, talking about another qubit, which is fluxonium qubit, and beyond. There are some type that it's beyond the fluxonium qubits. And then also I'll do a review or like take a look at the progress of fluxonium superconducting qubits recently. And finally, I want to introduce our research in the National Tsinghua University on fluxonium qubit. So let's talk about that. So to talk about the fluxonium qubit, first let me talk about this device. Okay, you need to talk about this, which is the Josephson junction chain. So the Josephson junction is happening in the previous two talks. It had already been introduced, and so I want to talk about another property of this Josephson junction, which is this connect inductance, or this inductance value associated with this Josephson junction in a unit area or in the unit length. It's quite large. It's very large compared to the geometric inductance. And so you can take a look that if you calculate it, well, typically this connected inductance is 3 order or 4 order magnitudes larger than the geometric inductance. So therefore, if you have a lot of Josephson junction put it together, well, you connect them all together, then this thing's acting as a large connect inductance. And also, because of the phase across this whole inductors is being shared, or like it's been divided to a small part of these small each Josephson junction, then actually the whole Josephson junction chain acting as a linear inductor in this sense. So this is one of the example that we made this Josephson junction chain with the Dolan bridge technique back into Maryland. Okay, so and then so with these each steps right here, the side view looks like you have we first deposit a layer of aluminum and then with the shadow mask, and then so you do oxidation in situ, and so you have native oxide form on this layer, and then you deposit another layer with an angle deposition, then you can form these Josephson junction right here, and then so the current flowing through need to go through all these junctions. So this is a large inductors. So with that, and actually now we have one more device, or one more components that can add it into the superconducting qubits. And so that's so the typical way to put it and then make it to become a fluxonium type of qubits is just shunted this large inductors to the original Josephson junction that shunted with the capacitor. So on the right-hand side right here, I write it down the Hamiltonian to describe this system. And so here the N and then phi operator associated with the charge across the capacitance, and then also the phase across the Josephson junction right here. And also then all these EC, EJ, and EL are the characteristic energy associated with this capacitor, Josephson junction, and then EL. And so all these parameters are engineerable, so you can tune it with a fabrication parameter. And so if we look at this Hamiltonian, actually this Hamiltonian just like a particle in a box. So the first term right here, you can treat it as a linear, as the kinetic energy terms. And then the second terms right here looks like the potential energy term. This is because the phase and the charge is following the commutation relation, just like a particle in the box, the position and the momentum's commutation